Hi everybody, I'm going to try my best to do a video lesson for section 9.1. We're starting a new chapter, chapter 9. And so the first section is about inverse variations. We have two objectives: to use inverse variation and to use joint and other variations. So I would like for you to take notes like we would in class for chapter 9, section 1, and then you're going to use those on our next lesson when I give you homework. That kind of goes with this. But right now we're just going to be going through these lessons and talking about the examples. Okay, in chapter 2, we studied direct variation. That was y equals kx. That was direct variation. You can also model with inverse variation, and it uses these following equations: xy equals k. So that's telling you to find k, you multiply your x and y together. You could also say y is equal to k over x if you just take that and solve it for y. We use that form anytime it asks us to write an equation. If it says write an inverse variation, we're going to say y equals whatever the k value is over x. We don't really use the third one very much, x equals ky. If you just took it and solved for x, that's what you'd have, but we don't really use that one very much. K cannot be 0. As with direct variation, k is called the constant of variation. And at the bottom it says you can describe an inverse variation as y varies inversely as x, or as y is inversely proportional to x. Kind of cut off at the bottom, but that's what that says. Okay, our first example says, suppose that x and y vary inversely, and x is equal to 3 when y is equal to -5. Write the function that models the inverse variation. So the way they did it, they started off with y equals kx. I just started off with k equals xy up at the top, because that's just the easiest way to find k. We have to find k first. So if you do k equals xy, that's equal to 3 times -5, so that means your k value is -15. Once you know the k value, just go down to the bottom and plug it in. Y equals -15 over x. That would be your inverse variation. Find your k value, plug it in on top of the x. Remember, with direct variation, it was y equals k times x, but inverse is y equals k over x. That's the biggest difference between direct and inverse. So for these inverses, you're just going to put your k value over your x. Remember, you can pause this video at any time so you can stop and catch up with the notes. Unlike in class when I talk too fast, you can actually pause this and make sure you keep up with your notes so that you have good notes to follow when you're doing your homework, okay? Next slide. Example just like that one. Suppose that x and y vary inversely and x is equal to 0.3 when y is equal to 1.4. Write the function that models the inverse variation. So find k. K is equal to x times y for inverse variations. So you would multiply 0.3 times 1.4 and you get 0.42 as the k constant of variation. So your equation would just be y equals 0.42 over x. Okay, next example, it says, is the relationship between the variables in each table a direct variation, an inverse variation, or neither? Write the functions to model the direct and inverse variations. So letter A, first thing you want to do is check to see how are x and y relating to each other. So in box A, in table A, the x numbers are getting bigger. It goes from 0.5 to 2 to 6. But the y values are also getting bigger. They're going from 1.5 to 6 to 18. If x is increasing and y is increasing, then that could be a direct relationship. Direct relationships always do the same thing. If x gets bigger, y gets bigger. So you want to check to see, is that a direct relationship? And the way to check is to see, do you get the same k value with each pair of x and y coordinates? So remember that the k value for direct, you find k by doing y over x. That would be 1.5 over 0.5, 6 over 2, and 18 over 6. And each time you get 3 as your k value. So since you get the same k value every time, that means that is a direct variation. The k value is 3 and your equation would be y equals 3x. In example B, the x values go from 0.2 to 0.6 to 1.2. Those x values are also increasing, but this time the y values are going down from 12 to 4 to 2. So the x's are increasing and the y's are decreasing. When they do opposite things like that, you have to check to see if it's an inverse relationship. So inverse relationships, in order to find k, you multiply the x and y together. So in this one, you would multiply 0.2 times 12, and then multiply 0.6 times 4, and then multiply 1.2 times 2. And each time you get 2.4, every time. The constant of variation is 2.4, and it is an inverse relationship. So your inverse variation equation would be y equals 2.4 over x. Letter C, the x values are increasing. They go from 1 to 2 to 3. The y values are decreasing. So one's going up, the other's going down. You need to check to see if it's an inverse relationship. To check for inverse, you always multiply your x and y together. 1 times 2 is 2. 2 times 1 is 2. And 3 times 0.5 is not 2. It's 1.5. So as long as it's not 2, that means it's not an inverse variation. Even though 2 of them work, the third one does not. It has to be true for all 3 of the coordinates. So therefore, letter C is not an inverse variation. And it's definitely not direct, because if it's direct, they'd have to be doing the same direction. If x is increasing, then y would have to increase also. So that one is a neither. So you do not have to write an equation if it's a neither. Next slide just gives you 3 more examples exactly like those 3. So in letter A, x's go from 0.8 to 0.6 to 0.4, that's going down. In letter Y, 0.9, 1.2, 1.8, those are going up. If one's going down and one's going up, you need to check for inverse. So to check for an inverse relationship, that means k is equal to x times y. So 0.8 times 0.9 is 0.72. 0.6 times 1.2 is also 0.72. And 0.4 times 1.8 is also 0.72. So yes, they have the same k value for all 3 pairs. So yes, it is an inverse variation, and I forgot to write the equations on these, I see. So your equation would be y equals your k value, which is 0.72, over x. I didn't write that on there, but you need to write that on there. Okay, letter B. Let's see, the x's are going up and the y's are going down. So since x is going up and y is going down, you need to check for inverse again. So k would have to be equal to x times y. 2 times 3.2 is 6.4. 4 times 1.6 is also 6.4. 6 times 1.1 is 6.6. So therefore, it is not an inverse relationship because we did not get the same value every time. So since it's neither, you don't need to write an equation. Letter C. X's are going up and the y's are going up. So that means we need to check for direct. So we have to take y over x. That's how you find your k value, y over x. 18 over 1.2, 21 over 1.4, and 24 over 1.6. Each of those is equal to 15. So since we got the same answer every time, our k value is 15. It is a direct relationship. And again, I did not write the answer, but the equation for that, since it's direct, it's y equals kx. So y equals, your k value is 15. So it'd be y equals 15x. That is the equation for letter C. Okay, next example. It says, heart rates and lifespans of most mammals are inversely related. Use the data to write a function that models the inverse variation. Use your function to estimate the average lifespan of a cat that has a heart rate of 126 beats per minute. So if you look at the table, it says a mouse, its heart rate is 634 beats per minute, and it has a lifespan of 1,576,800 minutes, and so on. And it goes down to the smallest heart rate is a horse, and its lifespan is 15,768,000. So you can see as the heart rate gets lower, the lifespan is getting higher. So that has to be an inverse relationship if there's a relationship. So you can see over here with their equations, they let R be the heart rate, S be the lifespan, and R times S would be how you find your K value. So they multiply the X and Y values from the tables together. And they're not always gonna be exactly the same when you're doing a real life example, but they say they're approximately, that's what those little squiggly lines mean right there. It says R times S is approximately a billion. So if you substitute, it says we have to find the lifespan of a cat that has a heart rate of 126 beats per minute. So they plugged in 126 for the heartbeats times S equals a billion for the K value. S is about 8 million. So a cat's lifespan is about 8 million minutes, or around 15.2 years. Next slide. Why is it not going on? I don't know. Let's try it this way. We'll go this way. Okay. Skipping that slide for you. And this is on objective 2, using joint and other variations. Okay. So quantities can vary with respect to each other in different ways. For example, y can vary directly with x cubed, y equals kx cubed, or inversely with x squared, y equals k over x squared. It's possible for 3 or more variables to be related. When one quantity varies with respect to 2 or more other quantities, the result is called a combined variation. We did talk about this with direct variations also. We talked about joint variations at that time. For example, a variable z can vary directly with both x and y. You can model such a joint variation with the equation z equals kxy. It just has the k value in there, but it has an x and a y because it's joint. It's direct with both of those. So just remember, joint variation means direct variation, but with more than one thing. Z varies jointly with x and y would be z equals kxy. If z varies jointly with x, that means directly with x and y, but inversely with w, you would write that as z equals kxy. That'd be the jointly with x and y, but inversely with w means that one's going to go on the bottom. And the last one says z varies directly with x. That means x goes on top with the k value, and inversely with the product wy. So that means both of those, the product wy goes on the bottom. Okay, so z varies jointly with x and y means z varies directly with the product of x and y. We just talked about that. So here's an example. The volume V of a tetrahedron varies jointly with its altitude h and base area b. A tetrahedron with a 5 centimeter altitude and a 6-inch square base has volume of 10 centimeters cubed. Which formula models this joint variation? So V equals K times capital BH. That means volume equals the K is the constant of variation times the base area times the height. So just plug in the numbers they gave you. It says the volume was 10, so they put 10 for the V, equals K times, and then it says the base area was 6 square inches, so they put 6 for the capital B, and then the height was 5. So 6 times 5 is 30, so 10 equals K times 30, divide both sides by 30, so 10 over 30 reduced to 1/3, so 1/3 is equal to K. That's your K value. Mail keeps popping up. Okay, so K is 1/3. So once you know that, go back up to this equation right here and just put in 1/3 where the K was. So you have volume equals 1/3 capital BH. That formula should look familiar when you learned volume, that all pyramids have a volume of 1/3 capital BH. That would be all pyramids. So let's try this one. I worked it out on here. The volume of a square pyramid with congruent, meaning equal edges, varies directly as the cube of the length of an edge. The volume of a square pyramid with edge length of 4 is 32 radical 2 over 3. Find the formula for the volume of a square pyramid with congruent edges. So since it's direct, we're using the equation y equals kx. Okay, so it gave you the volume. The volume is 32 radical 2 over 3. I can't put radicals on when I type, so I had to draw that on. So 32 radical 2 over 3 is the volume, equals K. We need to find K. It says it varies directly with the cube of the length of an edge. So we took the edge length and we cubed it, although my 3 got a little off. It's supposed to be over here. I think I can change it, maybe. Maybe? It's not letting me move it. I can't hold the camera and do that at the same time. Okay, so we'll just leave it. So 4 cubed is 64, that's where the 64 came from, and then to solve this, it's easiest since the side's a fraction to just multiply both sides by 1 over 64. So if you do 1 over 64, that 64 and the 32 are going to reduce each other. That'll become 1, this will become 2, so you just have 1 times radical 2 on top and 2 times 3 on the bottom. You end up with radical 2 over 6, that's your K value. So once you know your K value, you're just going to plug it in up here in your direct variation. So you end up, so the formula for the volume of a square pyramid with congruent edges would be y equals, or V, maybe we should have put V for volume, equals radical 2 over 6 times E cubed. That would be the formula for the volume of a square pyramid. Okay, and that is your last example. Not assigning any homework yet. So this video took about 15 minutes, so it probably took longer than that if you had to pause it to write down your notes into your notebook. The next assignment I give you will be the homework that goes with this. And then we'll probably do some IXL over this as well in with the homework. So hopefully you're not as bored as my puppy is right now. You wanna see where she's at? Let's see. There she is. Hey, Lucy. She's really excited. Here, let's see if we can wake her up. Say, hi, Lucy. Let me turn my camera around. Let's see. Is it gonna let me turn it around? No, it's not gonna let me turn it around. Okay. Say hi, Lucy. Say hi. She's a good girl. Okay, well, hope everyone is doing well. I don't know if you can see me or not. Hope everyone is doing well. I really miss seeing you guys in class. And let me know, reach out to me with an email if you ever have any questions on any of this stuff, okay? I'd be glad to help you. Take care. Bye.